Okay, so 5.6 is all about recursion and defining sequences recursively. So we've already done this. I showed you some earlier that were okay. For us to define this, first of all, I'm adding 12 each time, so it's arithmetic. That means, but I don't have to do that, but that's just what I'm doing. So if I were to do this explicitly, I would see that the nth term is given by 7 plus 12 times n minus 1. And that's how I define it explicitly. Recursively, I'd start with the first term. And to get to the nth term, I would take 12 and I would add that to the previous term. The previous term being n minus 1. And I'd add 12 to it. That is how I would do it. Okay. Sometimes we'll be given ones like this. Oops, sorry. T1 is 12. 12. And Tn is 3 times the previous one plus 5 or something. All right, cool. So then my first term is 12. My next one's going to be 36 plus 5 is 41. 41, stupid. The next one is going to be 3 times 41 is 123 plus 5 is 128, and so on and so on and so on. Okay. Now you're like, how would I do that problem? Okay, well, first thing I would try is I would get my calculator out. And I would try, first of all, clearly I'm not adding the same amount to each one. That's the first thing I notice. I am not adding the same amount to each one. Like I'm not adding 12 each time. Okay, so the first thing I would try here is I'd probably, let's divide and see what we get. Well, we see that's 3 point something. And then I'm going to do 41 divided by 12, and that's also 3 point something, but it's a different point something. You see that? So you're like, it's kind of weird. So if I'm given this number here, what I like to do sometimes is I like to subtract them and see what happens. Now, again, clearly it's not the same amount, but it might give us some idea of where to go. 29. Like, oh, wow. And of course, if I had the next one up the line, so 3 times 128 plus 5 is 389 minus 128, 261. And so if a fellow was looking at this and you're like, all right, here's my thing. And obviously, as I said, they're not like adding a constant amount like 5 or 2 or whatever. Okay. And we're not multiplying by the same amount each time, obviously. So then go ahead and try to subtract. But when I subtract these, what we call the first differences, I notice that, wait, this times this, that's 3. This times this is 3. Weird. Oh, interesting. So, in other words, it's 3 times the previous term. What does that give us? Well, 3 times 12 is, So I'm multiplying each time. I'm saying that there's a difference of 29. I mean, there's a difference of 3 times. The difference is 3 times something. There you go. Cool. And so I do that. I go, all right. So 3 times the previous term gives me, whatever it is. So 3 times 12 is 36. So 3 times 12 is 36. 3 times 41 is 123, and 3 times 128 is 384. Oh, these are so close to the actual values. What's the difference? Plus 5, plus 5, plus 5. That is a tricky one to do. They're very tricky. So when you run into ones like that, typically you're not going to have to, you're rarely going to have to be able to conjure one up that's that hard. Okay. Here's one. When you look at this, you're like, oh, interesting. Something maybe occurs to you. Let's go ahead and subtract them. 6 is the first difference. 12 is the next difference. 24 is the next difference. Oh, hey, wait, that's crazy. So look at that. I'm thinking to myself, all right. I'm multiplying in essence by 2 each time because the difference gets twice as big. So 2 times the previous term. 2 times 7 is 14. 2 times 13 is 26. Oh, geez, it's just this minus 1. And again, that was what we would say would be the nth term. How does that one differ from this equation? These are the exact same thing, this one and this one. The difference is where they start. So you need to specify we're starting at 7. That's our initial condition. Okay. Now, there's some fun ones. Of course, you've all seen this guy. The Fibonacci sequence. Where you go 1, 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 13, 21, 34, 55, 89. I can't remember. Dot, 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 dot. Okay? And so the Fibonacci sequence is only able to be defined recursively. Okay? There's no explicit formula for that guy. Okay? Sure. Yeah. So here is d sub n is equal to 3 to the n minus 2 to the n. Okay, and we need to show for integers bigger than or equal to 0 that the sequence satisfies the recursive relation dk is equal to 5dk minus 1 minus 6 dk minus 2. Okay? So what do we mean by that? Well, let's find out. So let's start with 0. 1 minus 1 is 0. Sure. Cool, I guess. And then it says to start with, tell me where to start on this guy, though. Okay, let's go ahead and find our first bunch of terms here, okay? So put a 1 in there, you get 3 minus 2 is 1. Let's put a 2 in there, you're going to get 9 minus 4 is 5. You put in 3, you're going to get 27 minus 8 is 19, I believe. One more time. 81 minus 16. I can't do that in my head anymore. 65. Okay, dot, dot, dot. So the question is, does this get the job done for us? Okay. So for 5, let's look what happens here. Okay. So I take 5 times the one just previous. So 5 times 1 minus 6 times the one way back, 2 back. So 5 minus that, yep, check, it works for that guy. Awesome. Okay. Note that you'd have to tell me D1 is 0 and D2 is 1 to pull this off. To find 19, let's see what happens here. So 19, well, that'd be 5 times 5 minus 6 times 1. 25 minus 6 is 19. Awesome. Let's do 65 just for a good time. So that would be 5 times 19 minus 6 times 5. This is 95 minus 30 is 65. Hot dang, it works. It's awesome. Okay. So they're not terribly difficult at all. You're going to be doing a lot of either showing that this, and really, honestly, I'd be very angry if you do not include the very first 2 things. The reason they didn't include that is because they wanted you to find them, I think, first, okay? So notice that if I had started with 10 and 11, I would get a wildly different set of numbers in these guys, yes? So it matters where I started. Okay, so make sure that you'd always define the first term at least. Sometimes you need to do the first and second and third and so forth terms as well, okay? I think there's one more I wanted. I wrote some down to do. Yes, excellent. So let's look at number 15 here. It says for the sequence of Catalan numbers, okay, is defined, prove that for all integers n bigger than or equal to 1, Cn is equal to 1 over 4n plus 2, and then the combination of 2n plus 2 over n plus 1. Okay, now the Catalan numbers were in exercise example 5.6.4. If I can find that, I marked it somewhere. 5.6.4. Yep, there they are. Okay, and so so the actual so we need to prove that this is true, okay? That in essence, that would be the recursive definition. So the actual Catalan formula is this guy. Like that. Okay, so let's list out the first bunch of numbers here. So when k is equal to, now notice it's k equals 1 over 2. It's 2 plus 1 is 3 over 1 times 3. 3 choose 1 should be J did something wrong there. Did you write the formula? Oh, you wrote the formula down wrong, you dumbass. There's a problem. So it's 2 times 1 is 2. 2 choose 1 is 2, and so the answer is 1. If you did it for 2, you would find that it's 1/3. 4 choose 2 is 6. 2 is your answer. C3, 1/4. Be 8, choose 4. I don't know what that is off the top of my head. No, dummy. What are you doing? $70. So the answer is what are you doing? Okay, you're fine. You're fine. No, wait. C3. Come on, Jay. You can do it, buddy. Maybe, dumbass. Let's try that again. Let's back up and see. Oh, that one was right. Sorry. That one's correct. Let's try this one again. Let's see if we can do it right this time. Stupid. So 1 over, now we're on 3, so 1 over 4. That's true. So this is going to be 6 choose 3, and 6 choose 3 is actually 20. If we did things right, it would actually work out. Okay? And so this is a job for, to be quite honest with you, Excel in my mind. Okay? So if it's me, this is the perfect reason to have Excel. If for no other reason, just, well, besides it's just a pivot table just for a good time or something. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Good enough for government work. So it's equals 1 divided by parentheses. And then it's what is it? This fella plus 1 times the combination of 2 times this fella divided by, or not divided by, comma, this fella. All right, excellent. Boom, done, done. Voila. Yes, the Catalan numbers, friend. Now, that's all fine and dandy. Now the question would be then, well, what would the next number be? In other words, I don't know. It's a good question. Let's find out, shall we? So, what we're saying is that this guy here is recursively defining this set over here, in essence, is what we're saying. Okay, so let me pause for a sec. Okay, let's just do this with the little bit of mathematical induction. I think I want to use. Okay, so We know it works for the first term. Okay, we assume it works for this one. Okay. Well, just a minute. Yeah, actually, I don't want to use mathematical induction. What I need to be able to do is I need to be able to rewrite. I need to set these. I need to do some manipulations here and see what happens. Okay. So when you look at this bit here, okay, I'm going to rewrite this 1 over, and I'm going to, and for no apparent reason, maybe at first I'm going to factor out a 2. It's going to give me 2n plus 1, I believe. Is that right? And then remember, what is this? Combinations, right? Well, combinations are the idea that you would take where it's n choose r is equal to n factorial over n minus r factorial times r factorial. Okay? So in our case, it's going to be 2n plus 2 times 2n plus 1 times 2n times 2n minus 1, and so forth and so on and so forth. Okay? Dot. But now I'm going to take these two and subtract them. So I'm going to get 2n plus 2 minus n minus 1. So it's going to be n plus 1, I believe. Is that right? You all see that? It's going to be n plus 1, n minus 1, dot, times n plus 1 factorial, which would be n dot. Cool. All right. So let's see what happens here. See if we can make some of this work. Okay, well, first thing I notice is I want to cancel that, but that seems goofy. So hang on a sec. Oh, no. It's okay. This right here is really n plus 1. Is that right? Times 2. So this can cancel off there. Okay. Hold that thought a minute. Yeah, I can cancel with this. This 2 can cancel with this 2. This guy can cancel with this guy. Okay, so far so good, right? So far so good. Now on top I have still 2n factorial on top. Does that make sense to everyone? Okay. On the bottom I'm going to have n factorial times n plus 1 factorial. And out front I got nothing. Okay. What I need to do is I need to beat this thing into submission a little bit better, because what I need to have, it needs to look like this. Now let's think about what that looks like. So there's 1 over, in our case it's going to be n plus 1. Okay, we need that out front. We don't have that yet. Now this is going to be, that's 2k factorial. So it's going to be 2k times 2k minus 1 times 2k minus 2, and so forth and so on. Okay. Now over, you're going to have 2k minus k, which is just going to be k factorial. So k times k minus 1 times k minus 2, times, and then times k factorial again. So k factorial again, which is k minus 1, and so forth. Okay? Dot. Well, right here, we have very similar to this. Can you see that? Okay, we have 2n factorial on top. That's what we got over here. We've got an n factorial on the bottom, but what we have here is we have n plus 1 factorial. Well, n plus 1 factorial is the same as n plus 1 times n factorial. So what I can do is bring over the 1 over n plus 1 out front, and then I'll have 2n factorial over n factorial times n factorial, which is another way of saying this times 2n choose n. Okay, and because we can work it out that way, we know that it works for all of them. Okay, if I could have done it with induction as well, but that was a pretty easier way to do it. I won't ask you to do one that gross on the homework, I promise. It's not the point of this class is you're not a math major, you are a engineer, software person. I want you to feel comfortable with some of that, but I don't need you to be proving stuff all the time. Okay? Again, the whole purpose of recursion, and I feel like you guys know this more than just about anybody, is the idea that, like for instance in Excel, the way I was able to drag this down, this is when we're doing it, but I could have also done something like this. I do this all the time when I teach classes on some finance. Okay, I routinely use Excel for this because it's awesome. But I can put up here your initial amount of your loan. Okay, and then now I'll just hard code it. I don't feel like doing it the way I usually do it, but then 1 plus our interest. Let's say you're getting a 4.5% loan, monthly interest, minus darn it, I should have made the payment. That would have been too easy. 0.045 divided by 12, comma 360, comma negative F1. Cool. And then drag this baby down. And this whole thing is predicated on the fact that I am using the cell right above the cell that I'm currently on to calculate how much money I will have or how much I will still owe next month. Obviously, how much I owe next month is based on what I owe this month. That's a problem. We made a boo-boo. J, you big dope. That has to be... Oh, give it to me, you dumb hippie. Oh, there you go. Hit the right one. There we go. No! F1. Dollar signs. There we go. Now let's try it again. Bam! 0. Beautiful. But look, every month, what I owe this month on this line 3 is predicated on what happened in the previous month. Ditto on line 6. We're looking back to the previous month to see how much stuff we had. That is the very definition of recursion. That is how that's how we use Excel a ton. Not always, but a lot. So I feel like I don't need to tell you guys that as much, especially software people. But yeah, I'm supposed to teach it, so we will. Good stuff.